Have you ever wondered how two uncharged metal plates in a vacuum can actually attract each other? The answer lies in a phenomenon known as the Casimir Effect, a strange and fascinating consequence of quantum physics. In this episode, we'll explore the science behind the Casimir Effect, its history, and its potential applications. Welcome to the podcast series called Quantum Bugs, where we discuss the latest discoveries and developments in quantum mechanics. In today's episode, we'll delve into the intriguing world of the Casimir Effect. This effect, first predicted by Dutch physicist Hendrik Casimir in 1948, is a quantum phenomenon that causes two uncharged metal plates in a vacuum to be attracted to each other. At first glance, this seems to contradict the laws of physics. However, as we'll discover, the Casimir effect is a fascinating and mysterious consequence of quantum mechanics, with implications for everything from nanotechnology to the nature of the vacuum itself. So sit back, relax, and let's explore the science behind the Casimir effect. Make sure to subscribe to never miss an episode. Next one is on quantum foam.
So, let's address the elephant in the room. What is the Casimir effect? First of all, it is a quantum mechanical phenomenon that occurs between two closely spaced parallel plates in a vacuum. It was named after its discoverer, the Dutch physicist Hendrik Casimir, who first predicted it in 1948. So, what exactly happens in this effect? Well, according to quantum mechanics, even a perfect vacuum is not completely empty, but is filled with virtual particles that constantly pop into and out of existence. These particles are pairs of particles and antiparticles, such as electrons and positrons, that briefly borrow energy from the vacuum before annihilating each other. Now, when two parallel plates are brought very close to each other in a vacuum, they can interfere with the virtual particles between them in a way that creates a difference in their energy density. In other words, there are more virtual particles outside the plates than inside, because some of the possible virtual particles between the plates are excluded by the presence of the plates. This imbalance in the virtual particle energy density creates a force that pushes the plates together, which is known as the Casimir force. This is a fascinating example of the weirdness of quantum mechanics, and it has been experimentally observed and measured to a high degree of precision. It has also been found to have important implications in a variety of fields, from nanotechnology and material science to cosmology and the nature of the vacuum itself. Make sure to subscribe to never miss an episode. Next episode is on quantum foam. The history of the Casimir effect. This effect is a physical phenomenon that occurs in quantum field theory, named after the Dutch physicist Hendrik Casimir, who predicted it in 1948. The effect is caused by the presence of quantum vacuum fluctuations, which create a force between two closely spaced parallel uncharged conductive plates. Casimir's prediction was based on the idea that the zero-point energy of the vacuum should cause a force between two nearby metal plates. He showed that the force would be attractive and would decrease as the distance between the plates increased. One of the most intriguing aspects of the Casimir effect is the appearance of Ramanujan's series in its mathematical description. Srinivasa Ramanujan was an Indian mathematician who made significant contributions to the field of mathematics despite having little formal training or access to advanced mathematical resources. One of his most famous discoveries is a series that can be used to calculate the value of the Casimir effect between two parallel plates. This series involves a summation of terms that correspond to the natural numbers raised to the fourth power. The fact that Ramanujan's series appears in the mathematical description of the Casimir effect adds to the mystique and fascination surrounding this phenomenon. It also highlights the deep connections between seemingly disparate areas of mathematics and physics. In the decades following prediction, scientists began to study the effect experimentally. In 1958, the first experimental verification of the Casimir effect was reported by Marcus Sparnay, a graduate student in the laboratory of Dutch physicist Johannes Diederik van der Waals. Sparnay's experiment used a torsion balance to measure the force between two parallel metal plates. Since then, the Casimir effect has been studied in a wide range of systems, including superconductors and dielectrics, and has been found to be an important factor in the behavior of microelectromechanical systems. In addition to its fundamental importance in quantum field theory, the Casimir effect has potential applications in nanotechnology and MEMS, where it can be used to create mechanical switches and other devices. Overall, the history is a fascinating one, marked by the insight and creativity of scientists like Hendrik Casimir and the many others who have contributed to our understanding of this important physical phenomenon.
The implications of the Casimir effect.
The implications are significant in the field of physics, particularly in quantum field theory. One of the most notable implications of the Casimir effect is the concept of zero-point energy. This theory suggests that even in a vacuum, particles are constantly fluctuating and have a zero-point energy that cannot be removed. It also has implications for the development of new technologies. For example, the ability to control and manipulate the Casimir force could lead to the creation of new materials and devices with unique properties. Additionally, the Casimir effect may have applications in the development of micro-electromechanical systems, which are used in various fields such as medicine and telecommunications. Furthermore, it has opened up new avenues for research in physics, particularly in the study of quantum fluctuations and the behavior of particles at the subatomic level. Scientists are continuing to explore the implications of the Casimir effect, and it is likely that its applications will only continue to expand in the future. Overall, the Casimir effect has significant implications in the fields of physics, technology, and scientific research. Its discovery has led to new understandings of the behavior of particles at the subatomic level, and has the potential to lead to the development of new materials and devices with unique properties. Make sure to subscribe to never miss an episode. Next one is on quantum foam.
Challenges and controversies. The Casimir effect is a fascinating phenomenon in physics, but it's not without its challenges and controversies. One of the biggest challenges is the difficulty in measuring it accurately. The force is incredibly weak, making it difficult to detect, and there are many factors that can interfere with measurements. For example, even the slightest contamination on the surfaces of the objects involved can drastically alter the results. Another challenge is the fact that this effect violates our intuition about how the vacuum should behave. According to classical physics, empty space should be completely devoid of any energy or particles. However, the Casimir effect suggests that there is actually a non-zero energy density in the vacuum. This goes against our common sense and has led to some controversy and skepticism among scientists. Additionally, there are debates about the theoretical underpinnings of the effect. Some researchers have proposed alternative explanations, such as the role of thermal fluctuations or the influence of quantum entanglement. These alternative theories have yet to be fully validated, and there is ongoing discussion and debate about their validity. Finally, the effect has some intriguing implications for fundamental physics, such as the possibility of extra dimensions or modifications to the laws of gravity. These implications are still being explored and investigated, and there is much to learn about this fascinating phenomenon. In conclusion, the Casimir effect is a remarkable phenomenon that has captured the attention of physicists and scientists for decades. It is a manifestation of the fundamental nature of the universe, where even seemingly empty space is teeming with energy and particles. The effect has not only provided a means for testing quantum field theory, but also has practical applications in areas such as nanotechnology and the development of micro-electromechanical systems. As researchers continue to study and refine our understanding of the Casimir effect, we can expect to see new applications and technologies emerge. The exploration of the effect also opens up exciting possibilities for our understanding of the universe at the most fundamental levels. Whether we are looking to improve our technology or expand our knowledge of the universe, the effect is sure to remain an important area of research for years to come. Make sure to subscribe to never miss an episode. Next episode is on quantum foam.
Thank you for listening to our podcast on the Casimir effect. We hope you enjoyed this journey into the world of quantum physics and learned something new. If you have any feedback or suggestions for future episodes, please don't hesitate to get in touch. And until next time, keep exploring the fascinating world of science and technology.